In this video, we will look at the multiplication rules for probability. Two events, A and B, are independent events if the fact that A occurs does not affect the fact that B occurs. Some independent events are rolling a die and getting a 6, then rolling another die and getting a 3, or drawing a card from a deck and getting a queen, replacing it, drawing another card and getting another queen. Multiplication rule 1 is this. When two events are independent, the probability of both occurring is the probability of A and B is equal to the probability of A times the probability of B. For example, a coin is tossed and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. The probability of getting a head when flipping a coin is 1/2, and the probability of rolling a 4 on a standard 6-sided die is 1/6. The probability of getting a heads and a 4 is probability of heads times probability of 4, which is 1/2 times 1/6, which is 1/12. 1 out of 12 times you perform this, on average, you should see a heads and a 4. Another way of finding the solution is to the last problem is to look at the sample space. Here we have heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. There are 12 possibilities, but only one, H4, gives the conditions we want. So the probability is 1/12. Another example, a card is drawn from a deck and replaced. Then a second card is drawn. Find the probability of getting a king and then a 7. Since there are 4 kings and 4 7s in the deck, the probability of drawing each is 4 out of 52, which is 1/13. Therefore, the probability of getting a king and then a 7 is 1/13 times 1/13. The probability of getting a king then a 7 is 1/13 times 1/13, which is 1 over 169, or about 0.006, 6 1/1000ths. Multiplication rule 1 can be extended to 3 or more independent events by using the formula P of A and B and C and so on is equal to the probability of A times the probability of B times the probability of C and so on. So for example, it was found that 3 out of 4 people who commit bank robberies are apprehended. If 3 robberies are selected at random, find the probability that all 3 robbers will be apprehended. The solution is, if R is the event a bank robber is apprehended, then the probability of R and R and R is equal to the probability of R times the probability of R times the probability of R, which is 3/4 times 3/4 times 3/4, which is 27/64, or about 422 thousandths, about 42% of the time. When the outcome or occurrence affects the outcome or occurrence of the first event affects the outcome or occurrence of the second event in such a way that the probability is changed, the events are said to be dependent events. Some examples of dependent events include drawing 2 cards from a deck without replacing the first, being a lifeguard and getting a tan, having high grades and getting an academic scholarship, parking in a no parking zone and getting a ticket. To find probabilities when events are dependent, use the multiplication rule with a modification in notation. The probability of drawing a king is 4/52, which is about 1/13. If we do not put the king back in the deck, the probability of drawing a 7 is not 1/13. It is 4 out of 51, which is slightly greater than 1/13. The probability of both events is then 1/13 times 4/51, which is 4 over 663, which is about 6 1,000ths again. It's not a big difference, but there is a difference. I believe that we said if we did replace it, it was 1 out of 169, which, if I remember correctly, is 4 out of 672 instead of 4 out of 663. So it's really not a big difference, but there is a difference. The conditional probability of an event B in relation to an event A is the probability that an event B will occur after event A has already occurred. For example, drawing the 7 after a king has been drawn but not replaced. The notation for conditional probability is probability of B given A. And we write that as P of B vertical line A. Multiplication rule 2. When two events are dependent, the probability of both occurring is P of A and B, the probability of A and B, is equal to the probability of A times the probability of B given A. So, for example, for a specific year, 5.2% of US workers were unemployed. 33% of those who were unemployed received unemployment benefits. If a person is selected at random, find the probability that they received unemployment benefits if they were unemployed. So the probability of unemployed and benefits is equal to the probability of unemployment times the probability of benefits given unemployment. Well, the probability of unemployment we see up here is 5.2% or 0.052. And the probability of benefits given unemployment is 33% or 0.33. We multiply those together, that's about 0.017. So there's about a 17 1,000ths or 1.7% probability that a person was unemployed and received unemployment benefits. To extend Rule 2 to 3 or more events, use the formula P of A and B and C and so on, which is equal to the probability of A times the probability of B given A times the probability of C given A and B, and so forth. For example, 3 cards are drawn from an ordinary deck and not replaced. Find the probability of drawing 3 jacks. Well, the probability of jack and jack and jack is equal to the probability of drawing 1 jack times the probability of drawing a jack given you've already drawn a jack times the probability of drawing a jack given you've already drawn 2 jacks. So that's 4 out of 52 times 3 out of 51, because there are 3 jacks left and 51 cards left in the deck, times the probability of 2 out of 50, because there are 2 jacks left and 50 cards left in the deck. So that's 1/13 times 1/17 times 1/25 when we simplify each of those, which is 1 out of 5,525, or about 2 10,000ths or 2/10ths of 1%. I'm sorry, 2 100ths of 1%. The probability of drawing an ace, a king, and a queen in order. We find the probability of drawing an ace, which is 4 out of 52, times the probability of drawing a king, which is 4 out of 51, times the probability of drawing a queen, which is 4 out of 50, because at each of these points we have 1 fewer card left in the deck. So that's 1/13 times 4 51sts times 2 25ths, which is 8 out of 16,575, or about 5 10,000ths. Tree diagrams can be helpful when events are sequential. So say box 1 contains 2 red balls and 1 blue ball. Box 2 contains 3 blue balls and 1 red ball. Find the probability of drawing a red ball. Well, we can look at the probabilities this way. The probability of drawing a ball, if we're flipping a coin to determine which box we draw from. Somehow that note didn't get into this, I apologize. But the probability of picking a ball from box 1 is 1/2. The probability of picking a ball from box 2 is 1/2. Then the probability of getting a red ball from box 1 is, that should be 4/6, not 2/6. No, that should be 2/6. It's 1/2 times 2/3, so that's 2/6. The probability of getting a blue ball from box 1 is 1/2 times 1/3, which is 1/6. The probability of getting a red ball from box 2, there's only 1 red ball out of 4 balls in box 2, so that's 1/2 times 1/4, which is 1/8. The probability of getting a blue ball out of box 2 is 3/4, so the probability overall is 1/2 times 3/4, which is 3/8. To figure out the probability of getting a red ball overall, we take the probability of getting a red ball out of box 1 and add to it the probability of getting a red ball out of box 2. That's 2/6 plus 1/8, which is 8/24, plus 3/24, which is 11/24.